Have you ever wanted to know if a battery is about to die? Or maybe if an apple is still fresh, but without, cutting it open? Well, there's a secret to it, and it involves a pretty amazing technique that lets us actually listen in on a material's invisible electrical signals.
I mean, it's a real challenge, isn't it? How do you see what's going on inside something complex like a high-tech battery, or even just a simple piece of fruit, without having to take it apart? How do you really check its health?
Well, the secret is to listen. You see, every single material out there has its own unique electrical fingerprint. And if we send in a tiny electrical pulse and then just listen to the echo that comes back, we can learn a ton about its internal state.
This incredible method is called electrical impedance spectroscopy, or EIS for short, and you can think of it as a way of seeing the invisible by using the language of electricity. So what is it, really? Think of it like a really sophisticated electrical checkup for a material. We apply a tiny alternating current, but we do it at different speeds, or frequencies. Then we measure how much the material pushes back. That pushback is what we call impedance, and believe me, it tells a whole story about the material's internal structure and its chemistry.
But here's its real superpower. What makes EIS so incredibly useful is its ability to analyze the interface. And that's just the critical spot where two different materials meet up. We're talking about where a battery's electrode touches the liquid electrolyte, or where layers in a composite material are joined. EIS lets us zoom in and see exactly what's happening in those super important zones.
Okay, so let's dive into this idea of impedance a little bit more. It's definitely more complex than simple resistance, but trust me, a good analogy makes it super clear.
So, what is the big difference between resistance and impedance? Well, think of it like this. Simple resistance, the kind you get with a direct current, is like water flowing through a narrow pipe. The obstacle is constant. But impedance, which deals with alternating current, is way more like an obstacle course. The difficulty changes depending on how fast you're trying to run through it, and that speed is the frequency of our electrical signal.
So what actually makes up this electrical obstacle course? It's really a combination of three different things. You've got resistance, which is basically electrical friction. Then there's capacitance, which is the ability to store a charge, kind of like a tiny temporary battery. And finally, inductance, which is all about how much a material resists a change in current. By measuring all three of these together, we get a much more complete picture of what's going on.
All right, let's step into the lab for a second. How does an EIS experiment actually work in the real world? As you're about to see, it's a very precise process. You really have to get the setup right to get data that actually means something.
So running an EIS experiment boils down to a four-step dance. First, you have to calibrate all your equipment to get rid of any background electrical noise. That's key. Then you carefully prepare your sample. After that, you're ready to measure. You run the test at a whole bunch of different frequencies. And finally, you plot all that data and start analyzing the results to see what story it tells.
And I can't stress this enough. That first step, calibration, is absolutely critical. As this quote from our source material makes very clear, if your initial compensation is off, you can end up with a completely wrong interpretation of your data. It is the foundation that the entire experiment is built on. Precision is everything in this game. The probe you use has to be perfectly clean, because even a tiny bit of residue can throw off the readings. The sample's shape and its size matter too. And you have to watch out for things like temperature, which can have a huge impact. It all goes to show that EIS is an incredibly powerful, but also very sensitive technique.
So you've done the experiment, you've been careful, and you've collected your data. Now what? Well, this is where we turn all those numbers into a visual story.
The final result is a graph, and we call it a spectral plot. On one axis, you have impedance, and on the other, you have frequency. It shows us exactly how the material's opposition to the current changes as we sweep through those different frequencies. And this graph, this is where all the secrets are hidden. Now, to really understand the plot, we usually break it down into three key regions: low frequency, mid frequency, and high frequency. Each section of that curve tells us something different. For instance, the low frequency part might reveal how ions are moving across an interface, while the high-frequency end can tell us about the properties of the bulk material itself. Very often, the graph will have this really distinctive, swooping curve, kind of like a slide. This is not a random shape. Its specific curve tells us a ton about the material, especially about its capacitive nature, how well it can store an electrical charge. By analyzing this curve, we can really start to understand the inner workings of the material.
Okay, so this is all really fascinating stuff for the lab, but so what? Why does measuring impedance spectra actually matter out here in the real world?
Well, it turns out EIS is used in a surprising number of places. In the food industry, it can check the freshness of meat by measuring how cell walls are breaking down. In medicine, it's used to develop new biosensors. And of course, it is absolutely essential for testing the health and performance of batteries, from the one in your phone to the one in an electric car, by monitoring that crucial electrode-electrolyte interface. Ultimately, the value of EIS is beautifully simple. It gives us a powerful and, this is key, non-destructive window into the inner workings of a material. It lets us see and understand processes we could never ever see with the naked eye, all without having to damage the sample.
So, from the health of your phone battery to the safety of the food on your plate, this technique is quietly working behind the scenes, telling us what's really going on. It really makes you wonder, right? As our tools for listening to materials get even more sensitive, what other invisible properties are we going to uncover next?